Good morning, everybody. My name is Chris Lee from the Distributed Sensor Systems research line. And today what I would like to do is introduce a few of our research strengths and highlights to you so that you can see what we've been doing for the last couple of years. Let me introduce a few of our team members. So there's myself on the left there, Harold and Jadella. We have other members as well, and the point to the slide is to let you see that we cover the full range of electrical engineering within distributed sensor systems. So no matter what sort of research project you have, we have the ability to contribute to it from an electrical engineering angle. To make that a little bit clear, if you look at our core competencies, it starts from the sensor system. So we have a sensor system with local processing, maybe some cloud computing, a user interface, and if it's a monitoring system, it ends there. If it's a control system, then you have to close the loop and put in the control system. And we have competencies at all these levels. To demonstrate that, I want to go through three projects, one that is about the sensor system itself, one that's about local processing and control, and one that is about model-based design, which is more like a systems overview and a system design technique. Okay, so let's talk a little bit about sensor development. We were given a project from a customer to put sensors, force sensors, 3D force sensors in a shoe. And these have to be very slim and small. And the problem was that the sensors on the market were way too expensive for the project budget. So we had to develop our own sensors. This is the concept we came up with. So what you see here are a set of capacitors that are cylindrical with a center pin. And when the center pin moves left and right, that changes the capacitance. And by measuring that capacitance balance, we can then measure the force. The physical product here was a 3D printed leaf spring system with the electrodes implanted in the center here. And then you could get a 2D force measurement out of this. Before we even got that far, we did modeling on this. So these are electric field modeling in 3 dimensions to show what the capacitance would be, how much it would change for a given force. And on the right here, you see the measurements that we made on the real system. You can see it's a little bit noisy. This is because with a 3D printed product, especially in plastic, it's a little bit rough. And so you get slip and stick. We now have a ceramic version of this, which does not have as much slipstick. So this demonstrates our ability to go from a user requirement to a concept to a working product in terms of really fundamental sensor development. From there, what I would like to move on to is the idea of control loops and local processing. And this project comes to us from a bike company that produces sensors and products for e-bikes. And what they want to do is they want to optimize the battery life of your e-bike. And they want to look at whether regenerative braking in an e-bike is something that is useful. Now, before you go and make an e-bike with a regenerative braking system, maybe it would be a good idea to model that and test it. So what we have here is we have a physical model where on the bottom here we have a motor that we can test, and on the top we have a mirror to that. And in this mirror, what we can do is we can provide a load that models a bike ride, maybe with wind, with hills, with braking, and with sudden stops, emergency brakes. Doesn't matter what. We can program this however we like, and then we can model the power uptake, how much power is used, how much power we could get back from regenerative braking. We can play around with the battery management system and change the control logic. All of this allows us to experiment with the model system without having to go to a full bike and test it in field. Alongside that, we have a physical model. So we have a model of what the motor should be doing, how it should perform as a generator, how much energy we could recover, things like that. So we have a model from which we can compare physical measurements, and then we can use that to adjust how we do our design work. So what we're doing here is we're coupling a physical test system in the lab with an electronic model, and between the two we have a cycle of development that you can use to optimize a system without having to go through expensive bike prototypes. And in that frame, I would like to move on to model-based design, and this is where we're sort of headed. So our example here comes from the medical world and a medical ventilator. They've been in the news a lot lately through Corona. Lots of people needed ventilators, and the problem with ventilators is not so much their expense. You know, the Netherlands is a rich country, it can afford a lot of ventilators, but you also need professional staff to run the ventilator, and you simply can't create those staff. You can't buy them, you have to train them. So what we were thinking of is, well, what if you had an intelligent control system for a ventilator? Then your staff wouldn't have to be so well trained, because your control system would do most of the work for you. And on top of that, if you're going to do that, then you can't experiment with such a thing on a patient. So you have to have a system that provides a model patient system. And once you have that, then you also have a training system for staff. So you can train people to use ventilators. And on top of that, the whole system becomes cheaper. So then you can have this in high volume, and because it requires staff trained at a lower level, then you can move it out to developing nations where the number of skilled staff is limited. Now, this is a bit what the system looks like. So at the top end, we have an electronic, a digital model. So this is a Simulink model that is that contains everything. So it contains a patient model, it contains a controller, and in the control system, we can put in whatever we like. So here we have the control system that is currently under development, but you can put in machine learning algorithms, deep learning algorithms. You can change this however you like, which means you can rapidly explore many different types of control systems and see which performs best. And to go with it, we have a cheap ventilator system. So this is the blower, the electronics required to control the blower, the sensor system, and attached to that will be a patient model as well. But the patient model is still under development. This is all put through a control system in an FPGA and a system on a chip, where we have a whole bunch of different parameters that are used to understand what the patient is doing and therefore what the ventilator should be doing. We are getting good results with this so far. So with a simple control system, we can match rise times, plateau pressure. We can't get the trigger level working so well. And the various other things are working properly as well. And the next step there will be to really put in a machine learning style algorithm so that you can remotely control this. And you take a supervisory role. And with a supervisory role, you don't need as much training. And that is the end goal, as I've said before. Okay. And with that, so to summarize, distributed sensor systems, what we do is we do end-to-end system development. So we can develop new sensors if they're required. Signal conditioning systems sit right in our wheelhouse. Doing local processing on maybe power limited processing systems. That's also things we can do. We also have experience with cloud processing, control systems, and of course the model-based design where you do modeling and code generation, hardware in the loop, model in the loop. That's all our thing. And with that, I would like to thank you for your attention and draw your attention to this afternoon where we have 2 tables that you can visit. These are tables where we have proposed research projects that we are looking for companies and partners to join us. These are, one of them is about monitoring plant systems to improve agricultural efficiency. And the other one is a wearable sensor to try and prevent people with diabetes getting foot ulcers, which can cause things like extreme sickness, amputation. If we can develop a system to prevent that, that would be very nice. And we would welcome your visit to our tables. So thank you very much for your attention.